Hey guys, welcome back to AlgoYogi, and let's delete a node in a BST. So let's go to the problem on LeetCode. Given a root node reference of a binary search tree and a key, delete the node with the given key in the BST. Return the root node reference. Now they've already said like there are two parts of this problem. First is search for a node to remove, which is key basically. We're going to search for the value key in our BST. We find the node and then we delete that particular node and return the root. So let's see how we're going to approach this problem. And there are quite a lot of ways of to solve this problem. There are a lot of ways that people take, and I am going to tell you the simplest. In our first example, we need to delete key 3. Now there are two parts to it that the problem has already asked us. First is find the node that has the value 3. Now we know this exists over here, and in a BST, the time complexity to look for a key is big of log n, which is also equal to big of h. Now, so how are we going to look for this key in our BST? And once we find it, then we will have to delete it. So I would propose a solution that would be basically looking for this key, and we can do that by comparing the root value. Basically, we're going to start at the root node and we're going to ask if my key is smaller than this root value. If it is, then I'm going to explore the left side. If it is bigger than, which it is not in this case, let's say I was gonna delete 7, then I would go to this side, and which would be comparing if 7 is greater than 5. So then I would go to the right side. So this is right, this is left. Now let's say I find it in big of log n time. Once I found my key node that I need to delete, I have to get rid of this node and return a node that basically holds valid our left subtree. So basically I have to replace this node, replace 3 with a valid value. And in this case they have shown us, if we replace 3 with 4, then it remains a valid BST. And how did they choose that? That's the trick. The trick is, we know using the property of a BST that the left values of a root node are going to be smaller than or equal to the root node value. But in the right side, that is, they're going to be always greater than our root node. Now I would say the only perfect value to replace my current node is the smallest value in my right subtree. If I want to replace this value with any value, any valid value, then it needs to come from my right subtree. And right subtree, basically the smallest value of my right subtree. So that's the entire problem. In the first case, in this example, there's only one value. Then we just simply return that value and place it the node where we're supposed to delete. Okay. If let's say this wasn't there, then we would return the left value. We'll just move this up. But in this case, it was present left and right, and we could just simply do that. Let's look at a more complicated example. That I have created here. And here things will become more clear. Since let's say, for example, I want to delete key 6. Now, to delete 6, I have proposed that to delete 6, we have to replace it with the smallest value in the right subtree. And how we do it? We're gonna go to our right and search for the smallest value, and that will also happen in big of log n time, and that value is 4. We will find it and we will place it over here and then delete this because we are using this value, and just delete this. That's it. That's what we have done in the first example as well. Now it's just we look for the value and then we use a loop to find the smallest value in my right subtree and place that value to the node that I'm going to delete, and just delete this or call the delete function on the node that was basically used, which was the smallest node, or maybe you can say the leftist node of my right subtree of the value that I'm going to delete. So let's implement it. Quite really simple, and as I write the code you will see that it's really easy to write, clear to the point that we have explained. So as we said, we're going to use recursion, and that would be if root is none, then we return none. Else if root dot value is greater than key, that means I'm going to find my key in the left subtree of this binary search tree. So what I would do is I will say root dot left would be coming from deleting this node. Basically I would just say self dot delete node on the root dot left and the key. That's what we're going to do. Elif, if the value is smaller than my root, that means it's going to be in my if the root value is smaller than my key, I'm going to look in the right subtree. And right subtree, basically I'm calling the delete function in the right subtree. Delete that node, go to that side. So you will return my root dot right from there. Now what's the else case remaining? That is if my current root is equal to my key node. So the key value node. So I have to delete this node. This particular node needs to be deleted. How are we going to do it? So let's say if we are at a node that we need to delete. So there are three cases that can happen. First is it doesn't have a left subtree. Then we return right node. Then we return right node, and we place it to the node that we need to delete. That's it. If it doesn't have right, so we return left, and that takes place of the node that we need to delete. If they both exist, then we enter into the while loop, searching for the smallest node in my right side, and which can be searched or leftist node in my right subtree. So let's do that. If not root dot left, then I return root dot right. Elif not root dot right, then I would return root dot left. That's it. Since we are replacing the root value, current root, so we just returning the root dot left or right accordingly. Else is the case, most important case that will run in most of the cases. So this is not like edge cases. These are the edge cases we have covered, right? So this is where we say, let's take the current node, and that would be root dot right. Okay, root dot right, and now I have to keep going down to the smallest node, which is the leftist node of this particular subtree. So if cur dot left, then I'm gonna assign my current as cur dot left. Keep going left until you come across a value which is not none. That's why I'm checking the condition cur dot left should exist. And okay, so now what we gotta do is, now my root dot value would be my current dot value, and I have to basically the root dot right would be left will remain as it is. Root dot right would be, I will call the delete node function. I'll call this function I'll call this function on my basically root dot write, but what do we need to delete now? We need to delete the current dot val, because we have already used this value for my root now. It's just I need to go to my root dot write now and go there and delete that value, and that will basically be in the case where it will just simply exist and it will have both left and right none. So this will just return none. This will return none to my like the place where I'm actually calling it on root dot write, and simply in the end I will just return the root. Okay, so let me zoom out and try to run this. Let's go over again. If root is none, return none. If root is basically greater than key, that I have to look in the left subtree. Otherwise, if it is smaller than key, that means key will be found in the right subtree, because right subtree has the greater values. Otherwise, if there is no left, return right. If there is no right, return left. If they all of them exist, just like we have seen in our bigger example that I was trying to show you. You can check that out if it's not making you sense. Then we gotta find the smallest key in my right subtree. So I'll look for it, keep going left. Once I found the value, I'll assign that value to my root value, and from the right, I will basically delete that current value now, because I'm using it. I'm placing it at the place where I'm deleting the node that I have to delete, and I'm using that smallest value from the right subtree, and then I return root. Let's see. Okay, this runs, and let's try to submit it. Awesome, 100%. So let's write down the time complexity here. Time complexity, we have already talked about it. It's a BST, and we are pruning perfectly, and that is something that we have to always take care of when we are solving a BST questions. In most cases, the time complexity will be big of log n, where log n could be equal to log h, where h is the height of the BST. Now a space complexity is basically how many nodes are at a given point, max nodes are on the stack. That would be also big of log n. Simply you can replace log n with log h as well, because they are kind of replaceable. Okay, so let's go back to AlgoYogi and mark this true, and I will upload the solution over here, and you guys can have access to the solution. And so please make use of AlgoYogi and keep solving the problem. I will add 500 problems here, and this is the target that I have for next few months, that I will add 500 problems, solve all of them, upload the solution, and then once we are done with those, we will feel super confident about any coding interviews. Okay, we'll solve all the topics. Okay, see you guys in the next video, and bye bye.